You can start. We're going to talk about buildings today because they're primary consumers of energy across the world. Now, there are various ways in which the energy consumption of buildings can be reduced.
You need to keep telling slide number.
I'm on slide number 3. One such way is called energy breakdown. Imagine that instead of your monthly bill, if I were to tell you that how much each appliance is consuming, so this is what we call as an energy breakdown. Research has shown that giving an energy breakdown can help save up to 15% on the energy bills. Now, there are various ways in which energy breakdown can be given, but here we propose an energy breakdown matrix that for different homes, how do we break down the energy consumption for different appliances? And we're going to be reusing this matrix throughout the talk. In terms of the related work, slide 5, the most common or the most obvious way of getting an energy breakdown is by using plug load monitors. So for each appliance in each home, we install a sensor. This is clearly not scalable and would cost up to about $2,000 per home. Can we actually reduce all these sensors to a single sensor, which is a smart meter? This technique is called non-intrusive load monitoring, where we just measure the aggregate household energy consumption at the meter level, and we use source separation techniques to break down the consumption into different appliances. Now, this NILM technique is clearly considered to be more scalable than installing plug load sensors because this just requires a single sensor per home. But is it still scalable enough to give an energy breakdown to every home on this planet? So we ballpark the number of homes in the entire planet in the range of 1 billion or so. So we propose a billion building challenge, which means that can we give a breakdown to 1 billion buildings on this planet? Now NILM does not scale to this level because it requires a single sensor per home, which is a smart meter. Now, although governments and utilities have installed smart meters, they sample data at once every 15 minutes or lower sampling frequencies, at which rate NILM algorithms are normally not so useful. And a typical smart meter which samples at higher frequencies, at which NILM algorithms are typically used, would cost up to $500 or $1,000. So that figure does not work for 1 billion buildings. So what we propose is, instead of the smart meter, can we just use the billing meter, which is the monthly bills that we're already getting. And we can also use historical trends in them. And on top, use some static household properties such as the area of the home, number of occupants, the number of rooms in the home. Now, a lot of this information is already publicly available. For example, in the US through Zillow. Now, the intuition how our approach can work is the following: that similar homes have a similar per appliance energy consumption. For instance, if we look at these two particular homes, they seem to be very similar in the washing machine usage. I'm on slide 11. And these two are similar in washing machine usage because they have a similar number of occupants. So homes that have similar number of occupants might have similar washing machine usage. Slide 12. Slide 13, whereas homes that have similar historical energy consumption bill patterns might be similar in their air conditioner usage because the air conditioner is a big part of your total electricity bill. So we propose two different algorithms for breaking down the energy consumption in a scalable fashion. The first of which is called Gemello. So Gemello is a Latin word which means twin. The key intuition of Gemello is that from a set of homes which already have an energy breakdown, which we call as train homes, and for a set of homes which don't have an energy breakdown, called as the test homes, for any test home, can I find a twin home in the set of train homes? I'm on slide 19. The key thing to notice is that the test homes, which comprises a much larger fraction of the total homes, only has the monthly electricity bills as well as some static household properties, all of which are easy to gather and available as of today. And another thing to keep in mind is that our approach is not using any additional sensor. So, say we want to break down the energy consumption of this particular test home and we want to find out the energy consumption of the fridge. We look at the two most similar homes to this test home and we just estimate the consumption of a test home from the consumption of these two homes. We repeat the procedure for the HVAC. The key thing to note is that now a different set of neighbors is chosen as the closest neighbors or the most similar home to this test home for the HVAC. Now the reason is that different appliances will have different features for defining similarity. For instance, for fridge or washing machine, it might be the number of occupants, whereas for the HVAC, it might be the historical trend in the energy consumption. So going in this fashion, we are able to break down the energy consumption of this particular test home. I'm on slide 28. The feature set that we are using comprises of three different parts. The first is the static features, number of occupants, the area of the home, number of rooms. Second are raw monthly features. So we are using a 12-month historical energy consumption bill as a feature. And third are the set of features which we can derive from these 12-month historical energy consumption, such as the mean, the max, the median, and the range. Now, an important question arises that how do we figure out the optimal set of features for defining similarity for each appliance? Like, how do we know that that number of occupants is the optimal parameter for fridge versus some other parameter for another appliance? And how do we find out the optimal number of neighbors? So this can be done using the trained dataset itself, where we use the features, that is the number of occupants in the bills. How well are they able to predict which of these features will best predict the energy consumption for different appliances? And we use off-the-shelf parameter optimization techniques and feature selection techniques to get the optimal number of features. I'm on slide 30. Coming to evaluation, so we use the publicly available data set for our analysis. We use 57 homes for evaluation, which is, if you compare to all the previous evaluations done in the community, so it's about 3 to 4 times more than what previous evaluations have done. And this data set is from Austin, Texas region. Just for the giving the context to a local audience, Austin has somewhat similar temperature as Delhi. It's also a warm city. And this is using 12 months data collected in 2013. We're using two state-of-the-art NILM approaches as the baselines. And to these NILM approaches, we're feeding 15-minute smart meter data. Now, this notion of 15-minute comes from the fact that the quickest sampling rate at which smart meters today sample is 15 minutes. So this is the practical limit to which the NLM as of today can work. So these two state-of-the-art algorithms include the factorial hidden Markov model, which was published in AI Stats 2012 and latent Bayesian melding published at NIPS 2015. And we're using the leave one out cross-validation as the cross-validation strategy. In terms of the evaluation metric, we first find out the absolute error for each appliance, which is the difference of the predicted and the actual observed energy. We find out the normalized error, that is, we just divide the absolute error by the actual energy. By the way, I'm on slide 31. We find out the percentage error, and we finally convert this error into an accuracy term. Coming to the results, so our results where we compare against the best baseline shows that our approach Gemello is comparable or better across all appliances. Now, for the important thing to note here is that the baselines are using 15-minute data, whereas our approach is just using a single reading per month and is still able to get better accuracy with them. This seems to be counterintuitive, but there are reasons why such a behavior can occur. Firstly, Gemello has the advantage that unlike NIL, we are able to leverage the data from the entire region. So for NIL, you would just use a smart meter and a test home. Whereas in the current case, for a test home, we're able to leverage the data from the entire train set. Secondly, NIL methods are, because of the fact that source separation problem is typically considered to be hard, it fares poorly for complex loads such as washing machines, which have very different number of cycles, dryer, tumble, spin, and historically it's shown to be giving bad performance. The important bit to note here is that we have transformed the problem from a source separation problem, which is considered to be hard, to a KNN problem, K nearest neighbor problem, which is Gemello, which is considered to be much easier. But the question was that are we still better than the baseline NILM algorithms when they have access to higher frequency data? So NIL was typically evaluated on a 1 minute or 2 minute resolution, and we found out that we are still better. While at 2 minute resolution, the NIL methods are improving, but we are still comparable or better. The next bit we wanted to test was that how good can we actually go with Gemello. So since Gemello is a k nearest neighbor kind of matching algorithm, we we define an oracle as an algorithm which can brute force and find the optimal neighbor for each test home. And if we use this oracle, we can see that we have a scope of up to 15 to 20% more improvement with our current approach. So what this means is that if we are able to come up with a better matching function, we can probably do even better using the current approach. Or if we can define better features for defining similarity. And another important question, slide 36, that we wanted to test was that how many homes do we actually need to get reasonable accuracy? So this turns out that even with a very small number of homes, say only 7 homes in the train region, we're able to beat the benchmark algorithms. And as obviously as we increase the number of homes in the train region, the accuracy only improves. But Gemello has its own set of shortcomings. So this is the typical picture of Gemello that we've been seeing thus far. But in reality, this is not very often because we have missing data. Like the sum metering for certain streams can go missing, certain static features can go missing. So by default, KNN won't work in such situations. Thus, Gemello won't work. It does need some modification to be done. And the other limitation was that we had to manually specify all the features. Like when we looked at those feature sets, we had to manually specify them. So could there be other features which lie latent in the data set, which we are not able to express? Can we learn those features? And the third and the most important shortcoming is that, so for Gemello, when we predict for a given test home, we are only looking at a small set of neighboring homes. But can we leverage the entire data set to be able to come up with better predictions? So, for instance, we are looking only at the similarity, but how about the dissimilarity between homes? Because that also contains some additional information. Now I'll talk about matrix factorization, which is a second approach, which was basically created to overcome some of the shortcomings of Gemello. This was slide 38. Now on slide 39. A very quick primer on how matrix factorization would work. So it's been very widely used for the problem of movie recommendation. Say we have these 3 users and they have given the ratings for some of these movies. The task is to estimate the ratings for the movies which they haven't rated yet, which is to basically to complete or fill this matrix. So this is often done by an approach called matrix factorization, where we break down this matrix into two submatrices. The first of which is the latent factor for movies. So it might contain the information such as how much action content on a scale of 1 on 5 exists in each movie, or what is the length of the movie. So these are the hidden latent features corresponding to movies. And the second factor is the latent factor for users, which captures that how much of these latent factors are important or users have an affinity towards these factors. Slide 39. Say we want to predict the rating for this particular user, the first user for Toy Story. We'll be looking at the latent factor for Toy Story in the movies matrix and the latent factor for this particular user, and we'll be doing an inner product of these two columns of these two vectors to get the rating for this particular user. So, inspired by the success of matrix factorization in the domain of collaborative filtering movie recommendation, and because of the way it is fitting nicely into the problem, we decided to use it for the problem of energy breakdown. Slide 40. The advantages of over Gemello are like, firstly, it's the inherent ability to handle missing values. Secondly, because empirically, matrix factorization has been shown to be much better than KNN for the problem of collaborative filtering, movie recommendation. And our problem has some very similar attributes to the problem of movie recommendation. And thirdly is the key intuition behind using matrix factorization, that there is only a small set of features which can distinguish the energy consumption across a large number of homes. So these set of features could be the geography of the home or the response of a particular home to weather conditions. And our hope is that in matrix factorization, we are able to learn some of these features as latent or hidden representations. Slide 41. So we start with this matrix, which we've been using for Gemello, but we can't use static features in this matrix because the data must be homogeneous. So we need only the energy terms or the dollar terms in this matrix. We convert the matrix structure as follows. So we stack up the appliance energy consumption across the 12 months and the aggregate energy consumption across the 12 months. And we do this process for each appliance separately. The key thing to note here is, as we've done for Gemello, that the test homes only have the monthly electricity features here. Slide 44. What we apply here is a variant of matrix factorization called non-negative matrix factorization. The reason why we're using non-negativity constraints is because energy or electricity bills are inherently non-negative terms. So that constraint can better guide a factorization. Slide 45. So like we did for the movie recommendation case, the problem is to break down the energy consumption into latent factor for months, where an example for latent factor of months could be how an appliance uses energy across different months of the year. Whereas latent factor for homes could be something like the, the response of a particular home to, say, the weather conditions or how it behaves across different months. And we have not forgotten the static features. We are using these static features to better improve the factorization process. So this is typically called as the factorization machine. This was slide 47. We did the evaluation on data port dataset as before, but the distinguishing factor of this evaluation is, instead of the 57 homes that we were using previously, here we are able to use 5 and 6 homes, because a lot of the homes used previously had missing features. It's again the Austin, Texas region, 12 months data. And instead of the 2 baselines that we were using before, now we're using 5 baselines, which are 3 state-of-the-art baseline algorithms on 15-minute data. 2 of which we described and used before for the Gemello evaluation. And the third one is called a sparse coding approach, which is typically better suited for low frequency data, like 15 minutes or so. And this was a recommendation by the community members, so that is why we chose to use this. And then there is another baseline called the regional average. So the US government, over the years, it collects statistics on the proportion of energy consumed by each appliance. So say for each region, we have a proportion, say fridge consumes about 20% in Texas region. We have such figures. We just use those numbers to compute to compute a baseline, or just to compute how much approximate energy can be consumed. And we are of course using a modified version of Gemello, because the reason why we had to modify Gemello was that Gemello or KNN by default requires all the features to be present, but in the absence of all the features, we're using k-nearest neighbors on the intersection of features that are available for a test home. So for each test home, we look at the neighbors which have the similar set of features, and from that neighboring set, we find out the optimal neighbor set. And as before, we're using leave one out cross validation. We chose to change the metric again on the recommendation of members from the community. Slide 49, where we first calculate the fraction of energy consumed by an appliance, that is the ground truth fraction, which is the ratio of appliance energy consumption to the aggregate energy consumption. We do the same for the predicted energy consumption, and we calculate the RMS error between the two. In the results, we can see that matrix factorization is performing better or comparable to Gemello, and we also saw that it was better than the other baselines. So this was done on the 516 homes, which had some missing data as well. We also wanted to test on the 105 homes, which had all the features. So if we see previously, the performance of washing machine was almost at par, or it was at par with the other baselines. The reason was that Gemello does not work very well when we have a missing set of features. But when we went to the homes, the 105 homes in this particular dataset, which had all the features, Gemello accuracy again shoots up. The reason why matrix factorization was able to give accurate prediction was that it was able to learn latent factors which have some physical significance. For instance, one of the latent factors we learned for the HVAC had a direct relationship with the number of degree days. So the number of degree days is a physical concept which defines the amount of heating or cooling required in a particular region. So it's defined based on the observed temperature and a baseline temperature. And here we can see a straight line, which means that the latent factor which learned actually has some physical significance. And given that the HVAC is highly weather dependent, this latent factor is thus very useful for the factorization process, and thus leading to good results. But the work is not without limitations. The fundamental limitation, slide 53, of this work is that both Gemello and matrix factorization will work only on data from the same region. Say if I have to break down the energy consumption of a Bombay home based on data from Delhi home, we might have poor results because the set of appliances may be different, the energy distribution patterns may be different. The way we wish to do this in the future is to use techniques known as transfer learning, which basically transfer or transform the set of distributions across the regions. And this way we can super scale our approach to possibly all homes in the world. And secondly, we are in the process of building an energy breakdown application for everyone. So by everyone here, I mean potentially 60 million users in the US, which have an access to a program called the Green Button, which is a program by the US Department of Energy where all the home consumers are provided energy consumption in a standardized format. So all we need to do is to just to tap into this service. Now, we have shown that Gemello and matrix factorization, without using any additional sensor, just using the monthly electricity bill and some static features, to be better than NILM methods, which have had 35 plus years of research and using much higher frequency data. So this begs us to ask this question: that does this mean that NILM is a dead community, or does NILM have no future at all? We believe that this is not the way, and NILM does have a future. And the way we see NIM having a future is to have more actionable energy saving insights. So, for instance, slide 55, a general NIM algorithm might end up showing a pie chart energy breakdown, which might tell you that a fridge is consuming 11%, and it might tell you that it's say 5% more than your neighbors. But does that empower you to really understand where your energy is going or how you can save your energy? In contrast, if we consider actionable NIM, it might look like the following. Say, if we have power traces from two separate homes, from the home one we see that the high power state occurs once, whereas in home two the high power state occurs multiple times. So there is probably something going wrong in the second home, which is due to the fact that it has excessive defrost. So the kind of feedback we want to give is your fridge has excessive defrost. You need to get it repaired, and if you get it repaired, you can save up to 30% of the fridge energy. Slide 56. The way in which we can give such a feedback is that we look at specific features of the power side of the power time series to infer why the usage is high. So it should again be noted that previously we were just looking at the pie chart breakdown, but here we are looking deeply into the produced time series, which is the output of NIM. So we look into specific features, trying to identify why the energy usage could be high. Maybe it's the length of the duty cycle as one of the features, or maybe the actual power value itself. So the way in which fridge works, and I'm using fridge as an example of how actionable feedback can be given. Fridge is a duty cycle based appliance where the compressor turns on and off periodically, trying to maintain a constant temperature in the fridge. But defrost occurs every now and then and it consumes a higher amount of energy. Does anyone know why a fridge defrosts? Or does everyone at least know that a fridge has a defrost component? No answers to why a fridge has defrost. So as it means defrost, so to keep the fridge running more efficiently, all the excess frost that is formed is actually removed. And if you have to remove the frost, you have to introduce heat into the system. So when defrost happens, the compressor turns off and a separate circuit turns on, which introduces heat into the system, and thus it ends up consuming higher power value. But when you introduce heat into the system, the next few compressor cycles will also be longer because that excess heat now needs to be removed. So considering a fridge power consumption for say 24 hours, we break down the energy consumption into three components. The first, this is slide 61, the first is the baseline component or the component of the fridge energy consumption which is unaffected by either usage or the defrost cycles. This would typically occur in the night hours for normal people and maybe from 5 a.m. to 10 a.m. for grad students, because that is when probably they'll be sleeping. We calculate the defrost energy as the energy consumed in the defrost state plus all of the excess energy over and above the baseline that is consumed in the next few compressor cycles. And we also calculate the usage energy as any energy over and above the usage, over and above the baseline. Now we have broken down the fridge energy consumption looking at the fridge trace into baseline, defrost and usage. The key idea would be to give feedback on the usage as well as the defrost, trying to find out anomalous homes or homes which can have an improvement on these two sectors. We also wanted to evaluate an important question, that how good is the feedback when we're using the traces from plug load monitors versus how good is the feedback or how does the accuracy of feedback change going from a plug load monitor to current NILM algorithms if we use these traces produced by NILM versus the ground truth traces or the best traces which can be collected using the plug load monitors. We used 97 fridges, 58 air conditioners from Austin, Texas region. And we found out that out of the 95 homes, 13 can be given feedback about their excessive usage energy. So all the homes in the red have excess usage. For example, these particular homes have about 70% of the cycles affected by usage. So I don't know, maybe they have a small kid at home, or they're very lenient about it, or maybe even the door is sealed, does not close properly. So all these homes, if they can be brought from the outside of the ellipse region to inside the ellipse, they can save up to 23% of the fridge energy. But when we used NALM algorithms, we found that the accuracy of identifying homes needing feedback is fairly poor. So all the red homes which should have been outside the ellipse, some of these come inside the ellipse. These are all false positives, and the false negatives, and the false positives are the homes which should not have been getting a feedback, but now are getting the feedback. So the state of the three baseline algorithms, NELM algorithms that we use, have a poor accuracy in giving feedback on the fridge usage energy. Slide 68. We did the same process for identifying excess defrost, and we found that roughly one-fifth of the homes can be given feedback on excessive defrost. It can help save them about a quarter of their energy. Now, some of these homes have excessive number of defrost cycles per day, like 2 or roughly 2.5 defrost cycles per day compared to the median of 1 defrost cycle every other day. But surprisingly, in current state-of-the-art NEL methods are not even able to identify the defrost cycle. So we cannot even give such feedback. Forget about the accuracy of feedback. We cannot even think about giving such feedback with existing NEL methods. But when we look back at the accuracy of these metrics, of these three algorithms that we use for evaluation, on the standard metrics which are used in the community, we found that they are comparable or better than the state of the art. So this brings us to an interesting question that you can be better than the state of the art, on the traditional metrics which have been used in the community, but still the output is not actionable enough. So this is due to the fact that these current NIL metrics are focused on reducing the error of the pie chart. So the predicted pie chart, they're trying to get it as close as possible to the actual pie chart. Whereas for giving actionable feedback, we have to look at the specific features of the time series. As an example, the defrost rate. So this was actually what we felt that the community can explore the direction of using a different set of metrics which have a more actionable component in them. But we definitely saw that there is scope of energy saving, actionable energy insights when we are using energy breakdown traces. But current NIL algorithms are not able to do that. The final part of my talk is about a set of tools that we developed for our thesis, which actually was the set of tools used during the entire evaluation. And this came from the fact that when early into my research, there was no way in which generality of any NALM algorithm could be established, because different algorithms, different research papers use different subsets of data, use different data sets. So we released this toolkit called NALM PK, which provided 10 datasets in a common format. And there existed no open source baseline algorithms, which we again provided in the toolkit. And we also provided a suite of accuracy metrics. NIMTK has been very well received in the community in terms of 100 plus citations in less than 2 years, and multiple papers in the community have leveraged NIMTK as a benchmarking platform. And we're most happy about the fact that 3 users have contributed their algorithms to NIMTK as well as 7 users contributing their own dataset. So all of this effort was done by the users themselves without us taking any part in it. And we were also fortunate to win a couple of awards for NIMTK. Now I'd like to conclude my talk by saying that we started by looking at NILM, where NILM was thought to be the most scalable approach towards energy breakdown. But we discussed why the requirement of even a single sensor per home nullifies the possibility of giving an energy breakdown to the entire planet. So we looked at a proposed set of approaches which do not require any additional instrumentation. Instead, they just require instrumentation from the currently existing datasets. And they're still more accurate given the fact that they don't require any additional sensor. We use an approach called Gemello, which was k nearest neighbor based, and we use a matrix factorization approach, which, due to the fact that it can learn latent representations, gave better results. But we also thought that this is not the end of NEL. If we can give more actionable feedback, NIL can be again progressed as utility. NIL can still be progressed in terms of research. But unfortunately, current NIL methods are not good enough to give this type of actionable feedback, which we discussed. And that's also a direction for the community to pursue. With this, I'd like to thank everyone for attending the talk.
So, good, Nipun, you finished well in time. So, we have another 15-20 minutes. Let me just maybe
Last questions. That's okay. The final discussion.
Yes. So, if committee members have any questions at this moment, which they are fine to ask, given there are other people in the audience, you can go ahead. We will definitely have a separate session between us and Nipun maybe 10 minutes later.
Hello? Yes, can you hear me?
Yes, Rahul?
Yeah.
Yeah,
okay,
go ahead.
So I think you did a fantastic job. There's big transformation from your proposal to the defense document. The presentation was really well done. I think you brought across both what you can do and what are open challenges very well, and that overall demonstrates a good maturity and really knowing how research is is not just black and white of everything is good or bad. So given that, I have a couple of questions. So it seems like in the Gemello, it seems to the accuracy is much worse for, as you pointed out, these dryers and dishwashers, and than compared to HVAC and lighting. Is that mostly due to missing data, or the fact that these are also very infrequent batch loads?
Yeah, I don't think this is due to the missing data. This occurs mostly due to the fact that so there's more variation or more spread in the distributions for dryers, dishwashers. So given the feature set that we have, it is probably more difficult to get accurate neighbors or accurate estimates for appliances such as dryers and dishwashers. So I think what you've raised is an excellent question, and one of the limitations of our approach, that our approach will simply break when the intuition breaks. So our intuition was that similar homes have a similar per appliance energy consumption. But we can have two homes which are exactly similar in the feature space, but they have very different usage. This could occur due to any reason. Maybe they just had a guest, or maybe they had some other anomaly which does not occur in a set of features. So I totally agree with you that this is definitely a limitation which we've thought about a lot, but given the feature space that we have, we don't really have a solution towards this as of yet.
Okay, so I think so the other aspect is we know that this a lot of the data that you would get is messy data, it's missing data. Many times it's poor quality data, especially if you're getting sub-meter data, not just the monthly billing data.
Right.
So in that case, we found that there are obviously KNN and then matrix factorization are approaches, but you want to also look at some non-parametric approaches such as regression trees that allow you to, essentially with the regression tree, are going to sift through a lot of the data, and the poor quality data will just go to a corner of the tree. So that might be something you can look into. So the other question I have is a little bit more in terms of now the actionable, insights and what is actionable, right? So what you showed is like an anecdotal sort of approach with, okay, here if we consider, I'm just knowing the mechanisms used in a defrost cycle, this is what we expect to see, and so versus, another direction to go forward with would be how can you synthesize, energy recommendation, reduction recommendations, right? So, so I guess there are two parts to this. The question is that there are two aspects. One is you have predictive maintenance that are appliance level inefficiencies, like you showed, and then the other is human behavior.
Right.
And with human behavior, it's very hard to change it. It's close to rock bottom. So, what are your thoughts on you know understanding what would be actionable going forward?
So there are contrasting studies on user behavior. Like what immediately comes to my mind is a study by OPAR, where I believe you might have heard about this study, where they just showed that telling you how you're doing with respect to your neighbors, even just at a monthly level, just by giving you a frown face or a smiley face, has helped save about 2 to 5% energy at a very large scale. So that does actually they did show that giving feedback, at least comparative feedback, because the human mentality, whenever you show that your neighbor is better than you, so they'll automatically figure out ways to reduce their energy consumption. But I do see your point that the general user might not be very willing to change the behavior just for say $2 to $3 of energy saving. So that does remain a challenge.
Okay, so then the last question I have is, so now a lot of this is saying, okay, well, here is the past data, and based on your last monthly bill, I can just tell you how you performed and maybe why you performed like this. Uh, do you have any thoughts, or I would like to hear your thoughts on what would be mechanisms for predictive monitoring, where many customers want to know what is their bill going to be, in the next month, in the next 3 months. So using the matrix factorization and the weighting for, from historic weather data, etc. Uh, would you be able to build up a system that can do more predictive analytics rather than just retrospective analytics?
Yeah, the system in the so I'm thinking out aloud. The system in the current form is not optimized for, I think, for optimized for predictive maintenance. But I believe that, so that I think it's a very different set of science where they're using forecasting models, and I've to be honest not given a thought towards it. But it makes sense to think about how we can extend the matrix factorization model to just project how much energy was used previously. So matrix factorization in some senses can be thought of as a regression model towards energy breakdown. So given all the existing features or all the external features such as the weather and say the number of occupants, I do believe that there is a scope of giving some predictive energy consumption numbers also, and we can also do that at an appliance level.
Okay, that's all I have. Very good.
Prashant, Krithi.
Hi, Nipun. Good talk, and I wanted to actually follow up on a couple of things that Rahul was alluding to. I had similar questions. In your second piece, you presented results as percentage reduction in energy rather than percentage accuracy. Can you translate that to us and tell us a little bit about what kind of accuracy that resulted in? It couldn't make the connection. So how much accuracy you got as a result?
Right. Just give me a second. So, right. So we observed, I'll just tell about the error percentages. So we observed error percentages to be roughly about 3 to 12%. So 3 being the minimum error percentage for the loads having lower energy consumption, and 12 was the error percentages for the appliances such as HVAC.
Uh, can you compare that to the previous one? I did not quite follow what you just said. So there was question about washing machine and dishwasher having low accuracy. I had
Right,
noted the same issue.
right.
And how much did this improve? Where did you end up with accuracy with this approach?
So you ask, just to clarify, are you asking about the improvement in accuracy on matrix factorization versus Gemello?
That is correct, yes.
Right. So can you see the slide I'm projecting right now?
Yes.
So we observed that with respect to the best baseline, the improvement in washing machine was 31%. But an important reason why this number seems to be high for matrix factorization was that the baseline algorithms are performing really bad. And with respect to Gemello, which is k nearest neighbor, there's an improvement of about 31%. So these numbers are calculated relative to the best baseline.
I see. Okay. And my second question was just a follow-up on what you said in response to Rahul's question, which was you mentioned O power. Now, O power provides a comparison as opposed to telling you anything about the potential causes or any actionable recommendations.
Right.
And I was curious as to what you thought were things you could do better if you actually added not just a comparison to neighbors, but gave a cause of why you might be higher than someone else or what you could do about it. Because
Right.
in talking to real users, once my neighbor came to me and said, I received this letter, they said my energy bill is high, but I don't know why or what I should do. So that seems to be a common issue. And I
Right.
wondered if you had any thoughts on this.
Right. So there are two different parts to my answer. The first part is that, say, if we are approaching this problem just like OPA, where we just have the monthly electricity bill, where we can be better than OPAR or give a more direct feedback is also giving the energy breakdown at a monthly level. So instead of just the total frown or smiley at the aggregate level, there's much more information in telling that, 4 out of your 5 appliances are okay. It's like you're doing good compared to your neighbors. But this particular appliance, say your washing machine usage seems to be very high for your region and for, say, the number of occupants in your home. So this is probably not a very fine-grained information, but still better than OPAR. So we expect it to be at least comparable to the energy potential savings of OPAR. The second part comes from the actionable energy saving insights that we saw. So those actionable energy insights can actually even be very real time in nature, like in terms of the lights being left off, or in terms of the air conditioner set point is set wrongly. So that was also one of the analysis which we did, but in interest of time, I didn't discuss that. So one of our contribution was also to propose that was a method which can identify homes which need feedback on their HVAC set point. So these are the specifics, more detailed, actionable energy insights that can be provided to the consumer.
Got it. Thank you.
Right, and Prashant, if you were just to show you those numbers that you were asking, so these tables are showing the exact numbers. There's a lot of text, and that is why I
Okay.
just converted to the percentage improvement.
Got it. Thank you.
Krithi, you have any questions?
Yeah, I sent you a question by mail, but let me ask same thing now. See, there seems to be some possibility of sensitivity of the transaction time on the overall result. Because example, if I get data every 5 minutes versus every minute for the energy consumption, then the notion of similarity will produce different observations, right? That's what I understand.
I didn't fully get it.
So if you have data at 5 minute level and data at 15-minute level and data at let's say 1 hour level,
Right.
will the notion of similarity change
So
with this data of resolution?
right. So the notion of similarity is likely to change because the set of available features will also change. So at intervals of 1 minute sampling, like if you're sampling it once every minute, you'll get a clear pass stream and you might be able to see the entire fridge defrost cycle or the fridge compressor cycle. But say if you're sampling every hour, all of that is just going to get muddled into the noise. So you'll not be able to look at features such as step changes or fluctuations in power or appliances changing state. So these are the set of features which will lose prominence once we lower the resolution. But having said that, there is also a component that actually when we reduce the resolution, some of the noise also gets reduced. So there is a trade-off between these two. Increasing the There's a trade-off when we reduce the sampling rate.
Yeah, so does that mean, or doesn't that mean that you have to qualify all your statements about one method being more accurate than the other, or on the temporal granularity of the energy data?
So using the concept of information theory in that sense that if you're using smart meter data at 15-minute resolution, so clearly it has more information than a single reading per month. So it is up to the NILM algorithms how they use the 15-minute data, and maybe they just ignore a lot of features. But even when they're using 15-minute data, they're not able to give reasonable accuracy.
Um, so I don't know how to parse that sentence. Like, even at 15 minutes, the granularity they don't have accuracy. Is there any point in time, in terms of the time granularity or periodicity of the energy data, at which both would be about the same in terms of accuracy?
So, sorry, I didn't fully get you. Can you please repeat the question?
See, the data becomes more and more fine-grained and hence has more features that you can extract from it.
Right.
If you have finer grain data, right?
Right.
So at some point, the granularity that you have might miss out all the features, miss out the features that you're interested in observing.
Right.
So at that point, accuracy will be the same for both for any two methods of measuring whatever feature, whatever aspect you want to compare. Correct?
Yeah, I totally agree with you. And so, an important reason why our approaches are giving better accuracy is not because we're using lesser data, but actually we're using more data, but we're using this more data from a different set of homes. Whereas, so the formulation itself has changed. The NILM algorithms, they can only leverage the data in the given test set. Whereas for our approach, we can use all the data from all the available train homes. So for example, if say there are some changes in the weather pattern in a city, so the neighboring homes energy consumption data will be better able to reflect these changes than maybe just using the smart meter in a given test home. So just using this notion of more data from different homes is actually helping us to get better accuracy compared to using fine grained data from a single home.
Okay. Okay. I'll talk to you by through email after the session is over. Okay.
Right.
I still don't understand some of the nuances of this, so we'll follow up.
Sure. So we wrap up unless if there are any quick questions, one or two questions we can take up from the audience.
I want to just point out, I think this is excellent. And your organization, I think you really put in a lot of thought. Not just the quality of work, but I was very impressed with it. So I want to say that.
You didn't even need snacks.
Technical question somebody can ask.
यहाँ पे नहीं
So questions.
So I was very interested in this club level monitor versus. So was it a problem because you had, was it the algorithmic problem or was it the fact that the other one was a single point sensor?
Right.
So you had interference between
Right.
multiple appliances.
Right.
So did you, was it the NIM algorithms that were not working out
Right.
well or was it the fact that this is a distributed sensor versus that's a single point sensor?
So in some sense, both of the points you're saying are related. So the NLM algorithms perform bad because it's a single sensor and there are multiple of these streams, and the source separation problem itself is a very hard problem. It's also an NP-complete problem in many of the solutions that are considered. The important bit to consider is that on average we might be able to get a stream similar stream, but when we're just considering average as a metric, we might lose these very fine specific features. And that is why the traces produced by the NLM algorithms are not good enough for giving actionable feedback. So all the results, all the hard work in the community has been done to get the average error down.
So you're saying that the environment algorithms are based on the assumption that it's a single point sensor.
Right.
So they both are and both of them are basically the same.
Right.
The same root.
Can you also kind of consider or make the point that essentially the anomalous data or the kind of pattern that you're trying to pitch out from this work that this is an anomalous feature. You're not able to capture that essentially using the existing level algorithm. So that impulsive feature is not captured by the level
Right. So another way to put what you're saying is that, so when you actually cluster, even if you cluster this data, the fridge data, even into three states, what typically happens is that the two states of the compressor itself, a few power vary, so the defrost state still does not get assigned because the clustering will still try to get to the points which have more data. So this was one of the reasons why the simple NIL methods were failing, because they failed to even model the different states of the model.
Because of the lack of the training data.
It's not lack of the training data, because if you're just using a data-driven approach, the data-driven approach will like to fit the data best. It does not want to fit the distinctions that exist in the data.
Keeping the main motivation in mind, how well do you think your method performs better in a country like India where you don't have standardized, whether deployments of the appliances or even in neighborhood, the changes between the homes are highly variable.
Right.
And you have a very big home and a very small home within a neighborhood.
Right.
So how well do you think they perform? The accuracy would be there in country like India?
Right. So to study this exact question, we had actually submitted a proposal and we thought about it. In India, whenever we think about this kind of an entire problem formulation, the first question that we need to answer is, how do you select a subset of homes which you drain? And that itself is going to be a hard problem in India, because there currently exists no or little infrastructure. There exists no or little standardization in terms of even the standard electricity bills. Although we've done some parsing and some hacking and got that data, but in general, or even the standardization does not exist. So I believe that first of all, before going into the technical details of the approach, there needs to be some amount of effort involved by the governments and the startup universities to try and standardize this infrastructure. Like in the US, 60 million homes have access to this standard of their smart meter or their regular meter and energy consumption patterns. But I do believe that the problem is going to be more challenging in India. So we actually, when we did a deployment in India, we found out that the voltage fluctuations are very high. So in the US, if you want to measure the power consumption, you can probably just measure the current. Here you need to measure both the current and the voltage. So you need better sensors or more expensive sensors. The problem becomes more harder in the Indian setting.
And coming down to the latent factors, so are the latent factors depend on the number of, I'm not sure, so the number of appliances you have in a home or the kind of appliances you have in a home?
So we learn a different latent factor for each appliance, and that is learned from the data itself.
Okay, so how well does the difference in appliances? So for example, I use a 2-star rated AC or it's a 5-star rated AC.
Right.
So how well does it affect your method? Because you are not correctly using the appliance parameter.
Right.
And you are only looking at a monthly bill.
Right.
So how well is your accuracy dependent on the differences in the appliances? I mean, say against a 3-star rated AC versus a 5-star rated.
Right. Yeah, that's an interesting one. The problem with this, I could not test this hypothesis because I didn't have the appliance ratings in my data set. But if that additional metadata is made available, I would actually throw that into a matrix factorization model itself. So as we were using the number of occupants as a static parameter, I would also love to use this as a parameter.
Or, I mean, an interesting approach would be that if we take the salary, the total household income,
Right.
and which we may indirectly correlate that, look, if my income is high, I'm willing to spend more on a 5-star AC, right? Or maybe if I'm more educated, then I'm willing to spend more on a 5-star AC. I don't know. So there could be few other indirect factors, could be salary, could be education level, which if thrown into this thing, may actually incorporate some of those aspects indirectly.
So I have a question. You talk about transfer learning.
Right.
So how is it going to help in case of NILM versus your algorithm?
In case of NILM, we have smart meter data and we have appliance level data. So there the model needs to be tuned. For instance, a model built in Delhi might say that fridge consumes 100 watts when it is in the operation state, whereas say in Bombay all the fridges consume 120 watts. So this model itself will need to be tuned. Whereas in our problem formulation, the distribution curves of the monthly bills as well as the distribution curves of the appliance level energy, those need to be transferred. For instance, Bombay has moderate weather, so say the total energy consumption is only 100 units per month on average, whereas in Delhi it is say 500 units in the summers and say 20 units in the winter, something like that. The curves need to be matched and fixed.
So again, is it globally scalable given that there are different geographic conditions, different
Right.
temperature and
So the way in which a global deployment can be done is that we firstly leverage all the existing data sets. And a lot of companies are already doing small instrumentation, say 100 homes done in every city. And I believe that is somewhat the set of the number of homes that might be required. And even when we're doing actually something like transfer learning, we still require a small number of homes in that region, even to fine tune that model. So transfer learning is basically saying that instead of requiring 500 homes in each different region, you might just do with 100 homes.
Let's finish it here, and um, we will have a separate session between the committee members and Nipun for the time. Yeah, so there is some snacks next door. Something you were tempted to stay for longer.
It was very nice. I want to point out, I think the way you handle the interaction is very nice. I want to point out that shows, the details and the way you shows the depth of your understanding, deeper understanding. And actually, I wanted to go and share that. See, many times when I sit in interviews for faculty members, I don't know the subject. But you're still making assessment, and this is one of the assessments. How are you addressing questions? What kinds of things you know, and what is the response you guys have? This is a good point. Now, I'm very impressed actually at the way you dealt with it. It's usually you don't expect it at this level.
Thank you.
So let's remove if there's any other rabbits, personal rabbits. So
Everyone has
you
them.
and Kamin. We can quickly just do between three of us.
Kamin, can you hear us?